Hello, welcome back to CS560. So today we're gonna introduce the last algorithm for single source shortest path problem. It's called Dijkstra's algorithm. Um, so it's the name of the inventor of this algorithm. And let's look at this algorithm first. So as for the plan for this semester, next week will be the last week for lectures. So on Tuesday, we will cover the final chapter, and we will talk about NP completeness, about the complexity of algorithms. It's very theoretical contents, and but it's still some important concepts that we need to know. And for Thursday, uh, we will have a review for the final exams. And the final exams, according to the university's schedule, will be on December 15th. I think it's a Tuesday. And it will be in the similar formats as the previous two midterms. Okay, so we will finish the graph algorithms, advanced graph algorithms today. Okay, Dijkstra's algorithm. So it's for solving the shortest path, single source shortest path problem. So previously we went through the Bellman-Ford algorithm, and we actually found that Bellman-Ford is not that efficient because it needs to make V passes. And in each pass, we need to relax all the edges in the graph. So a lot of these relaxation operations, especially towards the end, can be not necessary because they don't actually change the um, candidates' values for the shortest distance at all. So Dijkstra's algorithm basically is an improvement, and it will use a more smarter data structure to help select the edge that will need to be relaxed rather than relax all the edges. Okay, so the inputs are basically the same. So it's a directed graph, but it has a constraint that all the edges are non-negative. Okay, and one more difference from the Bellman-Ford is that the Bellman-Ford algorithm can detect uh, the existence of negative weight cycles in the graph. So in that sense, Bellman-Ford algorithm is kind of useful because given a graph that you don't know the property in terms of whether there's a cycles in it, whether there are negative weighted cycles, then it is helpful for you to decide whether this is a valid problem whether this is a valid question to explore uh, shortest path for all the vertices. Okay, so in that sense, Dijkstra's algorithm has a stronger condition that needs to be satisfied. So there shouldn't be negative weights. All the edges should have non-negative weights. Okay, so the Dijkstra's algorithm will maintain a set of vertices. So it will return the set S as the results for the shortest path uh, for all the vertices. So the shortest path um, for all the vertices put together, they form a shortest path trees, right? Um, but it can also be represented. It can be also we can also put them into a sets, and the tree edges are recorded by the pi uh, attributes for each vertex. Okay, so here this set is just for the convenience of returning the final values. Okay, so what this algorithm does is to repeatedly select some vertex u. Okay, so u is from the remainder parts of all the vertices, because v is the total vertices. So v minus s means those vertices in the graph, but not in the set. Okay, it's in the remainder part. So this algorithm will repeatedly select from the remaining parts, and these vertex should satisfy that it has the minimum shortest path estimate. Okay, so the shortest path estimate is stored in the d attribute. Okay, the d value, and it will add that vertex to S, and then relax all the edges, leaving you. Okay, in short, we will find within the remainder parts, we want to find the vertex that has the minimum d value, that has the minimum d attribute, and then we will add it to uh, our final results, and we select all the edges, relax all the edges, leaving that vertex. Okay, so that's we can intuitively think of this process like because each vertex is only selected once, right? After a vertex is selected, it's put into the sets, and all the edges are relaxed also for once. And so that apparently make the whole process much more efficient than the Bellman-Ford algorithm, because only each pass is each edge is only uh, relaxed for once, right? It's not relaxed for multiple times. But also the constraint is also there. We need to select the minimum. We also select the a vertex with the minimum d value. So it requires us to use some uh, mechanism or use some data structure to conveniently select a vertex with the minimum d value. Okay, and we have already used this kind of data structure a lot of times. Some option that's uh, coming to the coming to our mind could be a minimum priority queue, right? It is a priority queue or a queue-like structure, but each element in that queue has got a priority score. And the vertex or the elements that has the minimum score, that has the minimum score will have the highest priority. That means the minimum value will be dequeued first. Okay, so this is exactly what we want, because we want to keep the remainder vertices in that queue, and we want to quickly extract the vertex with the minimum d values. Okay, so given that thought in our mind, we can quickly implement an algorithm like this. And first of all, initialization, right? We don't have much to say about that, because we want to we need to initialize the d values to infinity and all the pi's to none, right? And also we'll initialize the data structure, the set S to empty. That'll be the basket that we put our vertex into, and it will be finally um, returned. And then for the q value, the minimum priority q will be initialized with all the vertices in the graph. And then it comes a while loop. Okay, so this while loop will not end until the minimum priority q is empty. And that means we need to go through all the vertices uh, in order to find the shortest path for all the vertices, right? Because that is necessary. And within each iteration of the while loop, in line 5, we will extract a vertex from Q. Okay, so that is to select the vertex uh, with the minimal d values, and then we will insert that d into the set. Okay, And for each vertex that leaves the vertex u, for each edge that leaves the vertex u. So by looking at the adjacent vertices for u, we can actually examine all the edges that leave u, okay? And we can relax that edge by calling the relax operation from u to v together with the weight function, okay? So the Dijkstra's algorithm, actually it's quite uh, the way to implement it's quite easy. We just need to utilize some external data structure. And the whole code, I think we'll analyze its efficiency later, but we'll first look at some of its property. First, the while loop will iterate exactly v times because we go through all the vertices. And it's never inserts vertices into Q, right? So that's why the Q will only decrease in its size, okay? And each vertex is extracted from Q exactly once. Yeah, that's for sure. And so it's actually kind of related to the greedy algorithms that we talk about. So it's a greedy strategy because when it selects the vertex that has the minimum um, shortest path candidates, the shortest path estimate D, it doesn't, um, it is not, we're not sure whether these will lead to the global solution, the global solutions for all the other vertices. We just select the vertex that looks like makes sense for now, right? We just look at the vertex that is closest at the beginning, at this moment, but we don't look beyond, and there's actually no way to look beyond, okay? So it's kind of a greedy strategy that is used in this algorithm. All right, so as we usually do, we will look at an example here for the Dijkstra's algorithm. Okay, so we have 5 vertices, and after we call the single source initialization procedure, we have all the d values and the pi properties properly initialized. Okay, and also we need to put all the vertices in the queue. Okay, so for example, in these uh, 2-line tables, we have the vertices and their d values uh, demonstrated here, visualized in this 2-row table. Okay, so our S is also empty. Okay, so now in the first round, when we extract minimal priority queue, the source will be the one to be extracted because it has minimum, the only valid value for D. It's 0, right? So the S will be extracted. So the S set will be S, will contain only one source vertex. And we need to relax all the edges that leaves S, okay? So we have 2 edges. First one is from S to T, the second one from S to Y. So we need to relax 2 edges, right? So, and if we think of the relax procedure, and the relax will is a if condition, right? It's will examine the values of the t with the value of s plus the edge from s to t, right? That's the operation that will be executed. So as a result of relax st and sy, the d values for t will be 10 now, and the d value for y will be 5 now. That is the results. And if we look at the table or look at the queue, the minimum priority queue, then the values for y and t are updated, and the y is highlighted because it has the minimum value. So in the next iteration, y will be the elements to be extracted. Okay, now let's look at the next one. the the y will be extracted, right? When we extract y, we need to insert y into S, and we need to relax all the edges that leaves y. Okay, so we have y from y to t, from y to x, and from y to z. Okay, so these three edges we need to relax. So after relaxing them, we can find that apparently the x will be no longer infinity and the z will no longer be infinity. And the t is also updated, right? Because we have find that the relax operation find that if we go from s to y and the y to t, the total distance will be 5 plus 3, which is shorter than directly go from s to t. So the pi relationship will be modified. So we don't directly go from s to t. So that is some little change here. And if we look at the table again, there's only 3 elements, 3 vertices left, and now z has the minimum score. So the vertex z will be the next one to be extracted. Okay, we have 7. And we need to relax the edges that leaves z. Okay, we need to relax the edge from z to x. And actually, there is a um, um, yeah, so from z to x is the one we need to relax. Okay, so after we relax that uh, edge, the d values for x is also changed, right? So this one uh, original path is removed because it has greater, it results in greater estimates. Okay, so only t and x are left, and we will simply extract t, right? So t will result in the relaxation on tx and t to y. Okay, and that will change the values for x, because we find that it's a shorter path if we go through s to y to t and to x. It will be even shorter than go through s to y to z to x. Okay. All right. So lastly, after x is extracted, then it's easy to obtain the final shortest path tree like this. And um, at this point, the minimal priority queue is empty, and the set S is just the total set of all the vertices. Okay, so actually, I need to correct what I said before. We don't need to return the S, because all the changes are made in place to the graph data structure. We just need to use the pi attributes and the d attributes in the graph to extract all the path information. Okay, so that is how um, Dijkstra's algorithm work on this example. And because this is a very efficient algorithm as compared to Bellman-Ford, but we strictly speaking, if we want to use it, we need to prove that it is correct, right? And the proof of Dijkstra's algorithm actually uses the properties of the relaxation procedures or relaxation operations. So it's based on this theorem, okay? So the Dijkstra's algorithm, if we run it on a weighted directed graph that has no negative weights, okay? So this no negative weight is very important. So if there is a negative weight in the Dijkstra's algorithm, then probably we shouldn't use this algorithm. So for the graph that satisfies this property, uh, the Dijkstra's algorithm will terminate with all the d values uh, to be the theoretical minimum points, to be the theoretical minimal value for all the vertices. So this delta is the shortest path distance. Remember that we define the shortest path from the distance of the shortest path from S to U, the theoretical value to be delta. Okay. So how do we prove this theorem, right? We want to show that Dijkstra's algorithm is actually correct. Then it is sufficient to show that if at the time that the vertex U is added to the set S, if we can show that at that moment, the D values of U is already the minimal theoretical value, then we can show that it will never change at the end, right? Because this equality holds at all times after, right? Because we will not relax that edge in the later points, right? So, keeping that in mind, we want to show that whenever we extract uh, a vertex from the minimal priority queue and we add it to S, we want to show that at that time the D of U is already the theoretical minimal value. Okay. So in order to prove it, we will use the strategy to create a contradiction, right? So in order to construct some contradiction, we will let U be the first vertex for which that's its minimal value, that the estimate value doesn't equal the theoretical minimum points when it is added to S. Okay, so that in order to show a contradiction, we want to assume that, okay, the D value of U is not the minimal value yet. Okay, so let's see what will happen. So because there must be some shortest path P from the source to U. So we can, in our mind, we can imagine that from the source to that target vertex U, we can always draw some paths like this. Okay, we can see that the S and the X, they are already selected, they are already extracted, they're already in S. Excuse me. So I can use this path P1 to indicate the path from S to X. And we kind of decompose the whole shortest path into three parts, right? We have P1 here, which is connecting S to X, and P2 here is connecting Y to U here. And Y is something that connects X and U. Okay, so Y is the first vertex along the path, okay, such that it is outside S, and it is a predecessor, and the X is its is Y's immediate predecessor. Okay. So we kind of decompose P into these three components, first from S to X, and then X to Y, and the Y to U. Okay, and we assume that the U is the first vertex that its D values doesn't equal the delta, the theoretical delta value. Okay, so let's see what will happen. And because we let U be the first vertex that the D doesn't equal delta, so we must have that the D of X will be the D will be the delta at the time that X is added, right? Because that is our assumption. We assume that the U is the first one that breaks the condition, and X doesn't break that condition, right? So when X is added by the algorithm, by the definition of the Dijkstra's algorithm, after X is added, we need to relax the edge from X to Y, right? So that is the algorithm's definition. So now we need to use the property called the convergence property. Okay, if you look back to the previous slide, if you use the convergence property of the relaxation operation, if when x is added and xy is relaxed, then the d values of y will also be the delta from s to y, because we have the d of x is already the delta of from s to x. Okay, that's called convergence. That means we already find the shortest path from s to x, and then if we relax the edge from x to y, then that will make sure that we also find the shortest path from s to y. Okay, and that is quite obvious, I think. Okay, so now we can observe a contradiction. Okay, so because y appears before u on the shortest path, okay, and all the edges, and also this is important, also we have the condition that all the edges are non-negative, right? And y is also before u on the shortest path. So that will leads to the conclusion that the delta from s to y must be smaller than or equal to the delta from s to u, right? Because all the edges are non-negative, they are accumulative, and the y is before u. So the shortest path from s to u must be greater or equal to the shortest path from s to y, right? That is something we can naturally obtain from the condition. So we can have these inequalities. The d of y, which is the delta from s to y, should be smaller than or equal to the delta from s to u, okay? And by our assumption, the delta from s to u is also smaller than or equal to, lower than or equal to the d of u, because that is our assumption, right? So because um, both y and u are in the remainder parts, right? Both y and u now are outside the set, outside the gray region, right? So that means we must, when we choose u, there must be the d values of u should be uh, smaller than the y, smaller than uh, the the d of y, because when we extract the minimum elements from the Q, it is must be the u elements we being extracted. Okay, and but that makes uh, because the u d of u must be later smaller than or equal to the d of y. So combining with this inequality above, we must have that the d values of u must equal the d values of y. Okay, but it contradicts our assumption that the d of u shouldn't uh, equal the delta from s to u. Okay, so it is certainly a contradiction. So that's why our assumption is not correct. So that also proves the um, uh, proves the opposite. So we can conclude that the d of u is already the delta from s to u when u is added to s. Okay. So that is how we prove the correctness of the Dijkstra algorithm. And we also kind of showed why it is necessary to have a non-negative values for all the edges, right? Because we have the condition that all the edges are non-negative. So that's why we can have the inequality here. Y is before u, and since all the edges are non-negative, so we must have the d of y should be smaller than the d of u. But if that condition is not satisfied, then we will never have this inequality satisfied. Okay, so if there are some negative weights in the past, then we cannot have the delta from s to y is smaller than the delta from s to u, because uh, we cannot say that since y is before u, then the shortest path from S to u should be smaller, should be shorter. That is not the case because from the path, uh, along the path from S to U, there could be some negative weights, right? If if negative weights are allowed, okay. So if there are negative weights, then things will be messier. Then we cannot use the Dijkstra's algorithm to prove. We cannot prove the correctness of the Dijkstra's algorithm. Okay. So Dijkstra's algorithm, in the next slide, we will see that it is a much efficient algorithm than Bellman-Ford, but we also find that it must come with a constraints. We must have satisfy that all the edges are non-negative. We shouldn't have negative values. Okay. So in the running time analysis, let's look at the analysis here. And it maintains the minimal priority queue by calling three uh, operations. First is to insert, okay, right? Insert everything into the queue and extract the minimum values in line 5, right? And also there's an implicit decrease key because after we relax the edge, right? We need to, after we relax edge means that we have changed, it is possible that we change the d values for certain vertices. And after the d values is changed, then we need to um, um, maintain the order of all the elements in the uh, minimal priority queue, right? So, and also, since each vertex is added to S once, and each of its adjacent edges is also relaxed exactly once. So the whole for loop will iterate for E times, and E is the total number of edges in the graph, okay? And the decrease key is also called E times because it is associated with the relax operation. Okay, and so if we the performance or the efficiency of the Dijkstra algorithm actually depends on how we implement the minimal priority queue here. So if we implement the minimum priority queue, use minimal heap, right? Well, remember we can use a heap to implement a uh, minimal priority queue if we use the minimal heap, right? So if it is that a case, then the heap, building the heap will take that linear time, big O of V, and each basic operation will take big O of logarithm of V times, okay? And the extract mean will take v v v times, right? V times logarithm of v. Okay, so each decrease key operation will also take the logarithm of v times, and there are e such operations. So putting all these together, right? That is the determined dominant term. So the total running time would be something close to the big O of v plus e times logarithm of v, or big O times big O of e times logarithm of v, if e is significantly larger than v. So that's something we can use to analyze the as a conclusion for the running time for Dijkstra's algorithm. So we can find that compared to the Bellman-Ford, Bellman-Ford needs to make v passes, right? And in each pass, it will it relax all the edges for once. So for Bellman-Ford, it is actually big O of v times e, and apparently it's much more efficient uh, in Dijkstra's algorithm. Okay, but also we want to say that again, the Dijkstra's algorithm comes with a constraint that there shouldn't be negative weights in the graph. All right, and it can be further improved with a more efficient Fibonacci heap implementation, for example, instead of the minimal heap. Okay, So lastly, I would like to draw some comparison of Dijkstra's algorithm with the previous basic um, um, graph algorithms. For example, breadth first search and the Prim's algorithm. Prim's algorithm is for computing the minimal spanning tree. Okay, so oops. The similarity is that um, we maintain some empty sets and we incrementally insert vertices or edges into that empty set. And the sets actually correspond to the black vertices in the BFS. After we have explored all the adjacent vertices, then we will paint a vertex of black. That is a similar case in Dijkstra's algorithm. So, and both Dijkstra's algorithm and the Prim's algorithm will use a minimal priority queue to find the lightest or the smallest vertex given a set. Okay, and we need to add this vertex into the set, and we need to implicitly adjust the weights of the remaining vertices. That is something that's very similar. Okay, and both the Kraskos and the Prim's algorithms for minimal spanning tree and the Dijkstra's algorithm for the shortest path problem, they are all greedy algorithms because when they make the current choices, they don't have information about whether this will for sure lead to the global optimal solution, but uh, it will make the best choice for now in the hope that it will achieve the optimal choice. Okay, so they all kind of belong to the family of greedy algorithms. Okay, so that is for all about the graph algorithms. We're done with the shortest path problems now, and it's time to do the assignments. And the assignments is already released, so I think now you should be capable of solving all the problems in the question sets. And for next Tuesday, we will cover the last chapter for NP completeness. And for Thursday, we will do a review for the final exams. Okay. If you have any questions now, please let me know.
Professor, I have a question.
Yes.
It's regarding the assignment.
Yes.
So